Okay, so as you heard, I'm Conrad Moore, and my research was sponsored through the NSF REU, and I'll be talking about some of the mathematics behind the technique which we use to image stellar surfaces. So first of all, what is light curve inversion? What the light curve inversion program does is it inverts a photometric light curve, which shows how the intensity of a star changes with its rotational phase. So as it rotates, we're going to see changes in the brightness of the star. It takes that and it gives us a stellar surface, and it will show us where the star spots lie on the star, which are areas that appear dark to the rest of the star. They're like sunspots on the sun, basically. So first we have to divide up the stellar surface, and we divide it up into a bunch of spherically rectangular patches, and we index the patches by patch ij is the jth patch in the ith latitude band. We also partition it so that all the patches have approximately equal areas. Okay, so here we have a picture of the sun, and you'll probably notice that here at the center it looks brighter than it does at the outer edge, or the limb. This is due to a phenomenon known as limb darkening. This is because stars are gases, so we can see, when we look at a star, we can see a greater depth, optical depth, in at the center, into the brighter and hotter layers than we can up here at the outer limb. Now, I'm going to describe to you the forward problem. So we're going to assume we already know what the stellar surface looks like, where all the spots are on it, etc. So we know J is the specific intensity in the direction of the hour normal of some patch ij. So that's just the intensity along the normal of, and we assume we know all the patches. Omega is the solid angle subtended of the patch from Earth, but we don't worry too much about it because we're concerned with relative brightnesses on the surface. So we're just going to make omega proportional to just the projected area of that patch along the line of sight to Earth, and L corrects for the limb darkening, which I just mentioned. So if we know all of these, we know all the patches, so the intensity at some observation time k is summed up over all the patches, the product of the intensity of the patch, the area it projects, and the limb darkening, which corrects for what I just mentioned. So, however, we don't know what the stellar surface looks like. We're going the other way. So we want to get all the J's with our data of IKs, which are all the points in the light curve. So one way you could think you could do this is to just guess a bunch of J's, guess a bunch of stellar surfaces, go through all of them, and get the light curve, which I just described, you can do if you already know the surface. So just go through, get a bunch of light curves like the IK, and just try to find the one that best matches up with our data, which is IK prime. So this is our goodness of fit function here. So you could think you could just minimize that and just try to get these to be as close as possible. However, this isn't going to work because the light curve problem is inherently ill-posed because it's extremely sensitive to noise. To illustrate this, you can think of having a stellar surface peppered with a bunch of little bright and dark spots. As that rotates, you're going to see a little high-frequency ripple modulation in the light curve. Now, the problem is that noise also takes the form of a high-frequency ripple in our data. So when you fit as good as you can, you're also fitting to the noise, and you're going to end up with a surface that's peppered with a bunch of little bright and dark spots, which are just non-physical noise artifacts. So to overcome this ill-posed nature, we're going to use a common technique for solving inverse problems, and what we're going to do is assume something about the solution we want, namely that we're going to have a smooth surface. So what we do, instead of just minimizing g, we're going to define this objective function e, which is lambda, which I'll get to in a second, times our smoothing function plus g. Now, how the smoothing function is going to smooth out our surfaces is that a surface that is peppered with a bunch of little bright and dark spots, you're going to see a large variance from the average, as this is summed up over all the patches, which is going to make S big. But we want both S and G to be small. What the smoothing function also does is apply this Cij, which is going to apply a bias. Now the bias is greater than 1. The reason we define this bias term is that we want to see dark spots on a bright photosphere, because this is what we see on the sun, and we don't think there's bright spots on these stars. So how this works is if a patch has a given variance from the average, it's going to be more favorable to make that patch dark because it's only going to multiply through by 1 for the dark patch. If the patch was bright, it's going to penalize it with a greater amount that makes S bigger. So it's going to favor dark spots, which we want. And the lambda tries to give us this balance between smoothness and goodness of fit. Like we don't want to completely smooth out our star and just get a uniform sphere, and we don't want a bunch of noise artifacts. So we have to balance. Now, this is the procedure that LI uses to make a surface. Now, our desired goal is for our goodness of fit to equal our estimated variance in the noise. We only want to fit to as good as is justified by our noise. We don't want to overfit. So we define these two functions, little f and little g. And you'll notice that if f is equal to 0, then we'll have achieved this goal. Sigma squared, square rooted, we'll get 0. So also this little g here, when we make this equal to 0, here, this is our estimated ratio of the intensity of the spots to the photosphere on the actual star. This is based on previous estimations from other studies by other people of our star. So, and now you'll notice that this is going to be the darkest patch on our reconstructed surface, the minimum intensity patch, over the average of all the patches which we use for the photosphere. So when this is equal to 0, we'll kind of have a similar ratio to what we actually think the star should be. Now you don't have to get too hung up here, you can look at it in greater detail, it's on my poster, but basically it minimizes E with a conjugate gradient method, so it goes, LI goes around in multi-dimensional space, getting the proper J's, and then it goes through making these two equal to 0, probably repeatedly, so to get a good lambda and a good bias. So after it's done all this, we'll have a smooth surface where it's only fit, but it's justified by our noise. And the dark spot to photosphere brightness will be what we actually think it should be. Now, we actually take data through multiple filters with our CCD camera of our star. The reason we use multiple filters is because of limb darkening. Limb darkening provides this little bonus in that it will also give us extra information about where the spots lie on the star, because you'll see differences in light curves if there's different limb darkening. You'll see this is an exaggerated case of limb darkening, but the main thing is that the two light curves are different. So, and I'll illustrate this. You see, these are a bunch of simulated stars that we did, Dr. Harmon just made, and then ran it through the program to see what it gives us. You'll see over here, just taking this one, this is a high latitude spot, and now when we run it through using VVRI, you'll see that the spot moved up. It's got a better idea of where the spot lies because we're seeing different limb darkening through multiple filters. So, and then here's our 2008 results. This is the star LO Pegasi. So this is data we collected nights of July 1st and July 2nd, and here we have July 15th and July 16th. And you'll notice we've got what appear to be two spots here. And what's interesting is that this is different than previous years. We haven't seen two spots. Well, I haven't seen two spots in previous years, and it's the main difference is the light curve seems to it dips a lot more. So that's interesting. And that's it. So this was a question.
Is your noises, since the small spots look the same as noise, how do you know what your noise is? Do you tell them another source?
Well, we actually do kind of know what our noise is. There's readout noise from the when we load them into the software to analyze, and as it takes images. There's dark noise, which we accommodate for using flat field subtraction, and this answers your question.
If it was peppered with small, bright, and dark spots, we're not going to see that because it's lost in the noise. So we don't even try to find those.
So your smoothing thing tends to turn a bunch of small spots into one big spot? Is that sort of true?
No, what it's doing is it's getting rid of a bunch of what we believe to be noise artifacts. So there'll still be a big spot, but if you didn't use the smoothing function, you just get that in addition to a bunch of, like it'll look really messy.
So it's there to find the big spots, not the little spots.
Yeah, we wanted to focus on big spots.
In the graph with your brand new results. So is there something significant there? Are the two joining? Are they merging? Are we to take that? Yeah. In just the time difference between you've done that, is this?
It's kind of hard to
Could
say.
be. It could be.
Yeah, they could be.
It certainly visibly changed the shape of the light curve. And this thing rotates every 10.17 hours. So even looking on 2 successive days, it's, with some spots they change over rotation. So it may very well be that these spots change on time scale.
You seem to be missing some data in your curve there. I was wondering, what?
I was that one.
Just wondering what was going on there.
In that
Well,
phase?
it does, the star is rotating, so I mean, and we do have to go out at the same time, we can only observe it at night, so it just happened that it wasn't, we never saw that view from the star when we went out there.
We had 2.5 clear nights in a row, so to speak.
Okay, if there aren't any other questions, thank the speaker.